In today's video, we're going to look at solving logarithmic and exponential equations. First, we're going to look at these logarithmic equations, and there are two different types that you need to be aware of. First one is type 1, second is type 2. A type 1 logarithmic equation is where you are asked to solve this logarithmic equation which has just logs in it. There are no other constants in there. It's just going to be log base something of something equals log base something of something. The only thing that you have to be careful of in this case is that all the logs have the same base. If they don't, you would have to do a change of base, but I'm not going to give you anything that will require that. You just have to be aware that in order to solve these, all the logarithms have to have the same base. So a type 1 log equation is just an equation that involves all logarithmic terms. In order to do this, I'm going to show you some examples. I'm actually going to walk through the examples in the textbook for each of these different types of equations, just because the examples in the textbook are really good and show you exactly what you need to do. And I'll go through it step by step with you. So the first one that I want to look at is solving log base 2 of 3x squared plus 1 equals log base 2 of x plus 11. Okay, and I'm going to walk you through step by step of how we are going to solve this. Because logarithms are invertible, because they are one-to-one, because they are invertible, we could go ahead and invert both sides here by raising both sides as a power of 2. If you did that, you would just get the argument back. So the first step that you're going to do here is just to set the arguments equal to one another. So you would set 3x squared plus 1 equal to x plus 11. Okay, you can do that, like I said, because the logs have the same base, and that would be equivalent to raising both sides as a power of 2, which would invert the logarithm function by using an exponential and would just give you the arguments back. So the first step that we're going to do here is to set the arguments equal to one another. Like I said, this is a type 1 log equation because every single term on both the left and right hand sides have logarithms in them. The other thing that you will have to be aware of, which we'll do in the next example, is sometimes the logs on both sides won't be combined. So you will actually have to combine all the logs on each side before you go ahead and do this step, but we've already got that in this case. So we're going to set the arguments equal to one another, which will give me 3x squared plus 1 is equal to x plus 11. Then you can go ahead and solve for x. Okay. So if we do that, you bring everything onto one side, set it equal to 0, which would give you that. And then if you factored this thing, you would get 3x plus 5, x minus 2 equals 0. I would give you something easy to factor if you're doing this in an exam. This would be more of a homework problem, which may take you slightly longer to factor it. Once we've got that, we solve for x, so we get the two possible values for x are x is equal to negative 5 over 3 or x is equal to 2. Once you get to this stage, what I want you to do is to go ahead and plug these values for x back into your original formula. Okay. Remember, with logs, you cannot have a negative argument. The number in those parentheses cannot be negative, because otherwise, in this case, you'd be saying that 2 to the power of something equaled a negative number. So whenever you get these x values back, I want you to go ahead and plug them back into the original equation that you had, and make sure that when you plug those x values in, that none of the arguments are negative, because you cannot have 2 to the power of something equaling something negative, so those logs are not valid. It turns out in this case that if I plug in x is equal to negative 5 over 3 into 3x squared plus 1, you would get 3 times negative 5 over 3 squared, and that squared value will make it positive. So that would actually be greater than 0. And same when I plug negative 5 over 3 into my right-hand side, I would get negative 5 over 3 plus 11, and again that's greater than 0. So that tells me that x is equal to negative 5 over 3 is a valid solution. Okay? If you get either one of those would be less than 0, then that solution is not valid. We cannot use it and we get rid of that particular x value. But in this case, that is a valid solution to our problem. And you would do the same for x is equal to 2. And clearly we can see that when I plug 2 into 3x squared plus 1, I get a positive number, and same when I plug it into x plus 11. So both of our x values in this case give us a valid solution, but make sure that you plug those x values back into the original arguments to make sure that the arguments are positive before you go ahead and pick which ones are your solutions. Okay, one more example that I will do here just has that additional step at the beginning where we will have to combine some logs on each side before we go ahead and set those arguments equal to one another. So in this case, we've got the natural log of 2x plus 1 minus the natural log of x is equal to the natural log of 3. So like we said before, what you would do is you would set the arguments equal to one another. The problem that we have here is that we have multiple terms on our left-hand side. So I will need to combine those terms, so I just have one log term on either side, and then I can set those arguments equal to one another. Going back to our properties of logs, I know that if I've got two logs that have the same base and they're subtracted from one another, I can combine that into one log by saying that I've got the natural log of 2x plus 1 over x. That subtraction means that I can combine them into one log and do a division of those arguments. Okay. Now we proceed in the same way as before. So the first step is we're going to set those arguments equal to one another. That would be the same thing as raising both sides as a power of e, that constant. Like I said, that's like inverting that natural logarithm. Then you go ahead and our second step was to solve for x. So I'm going to multiply both sides through by x. I'll subtract 2x from both sides, and that will just leave me with x is equal to 1. If I go ahead, like I said before, you have to, for your third step, plug this back into every single one of the arguments from your first original equation, okay? And make sure that every argument is positive. So when x is equal to 1, 2x plus 1, that's positive. X is 1, so it's definitely positive. And then our last one is a constant, so you don't need to plug it into there. But all arguments are positive. When x is equal to 1. So that means it is a valid solution. If you ever find that an argument, any one of the arguments is negative for a particular x value, you cannot use that particular value as a solution. Now let's go on to look at type 2 logarithm equations. So this time, For a type 2 log equation, it means that some terms have logarithms in them, some terms don't. So we can't do like what we did last time, just combine all the terms on the left and the right and then set the arguments equal to one another, because you are going to have some terms in there that don't even have a log in them. So we can't do that like we did last time. So we've got to come up with another way of solving them. And again, I'm going to do this by examples and go through it step by step with you so that you can see how to do this for other examples. But a type 2 log equation means that some terms contain logarithms while others don't. Okay. How do we go ahead and do this? Okay, so let's do this example and I'll take it step by step to show you what you're going to do. So here we've got 2 log 2 x minus 1 is equal to log 2 of x plus 12. Okay. Your first step here is to collect all log terms on one side, all other terms on the other. Okay, so if I do that for this particular example, I'll take all my logs onto the left and all my other terms onto the right. So that would leave me with 2 log 2x minus log 2 x plus 12 is equal to 1. Okay. Your next step is to combine all the logs into one term. So using our properties of logs, I need to get this all into one term. I've actually got to use 2 different properties here. I've got a constant in front of this log. Remember that I can do the constant to exponents. So here I can take that 2 and make it a power of x. So I would have log 2 of x squared. And then I've got minus log 2 of x plus 12. Well, by doing that subtraction, I can combine them into 1 and take it as x squared over x plus 12. So the first thing I would do is do that exponent to constant or constant to exponent, whichever way around you're doing it, and take that 2 into that particular argument. And then I would look at that subtraction and I would say, okay, that means that I can combine them into 1 and do a division. So my left-hand side becomes x squared over x plus 12 and taking log base 2 of that. Okay, so I've used 2 different properties there. The third thing that you're going to do is to raise both sides as a power of the base of that log. So that means that I take both sides as 2 to the power of the left-hand side and 2 to the power of the right-hand side because my base of my log is 2. That's pretty much what I said we were doing back here with our type 1 equations. Let's look at what we had here. By setting those arguments equal to one another, the reason that I could do that was I was basically inverting my log by raising both sides as a power of my base 2. So I was saying that my left-hand side was 2 to the power of log base 2 of 3x squared plus 1. And by our properties of logs, that just gives you the argument back, because by raising it to that particular base, you were saying, okay, I'm taking an exponent, an exponential, and that log, putting them together, and they're inverses of one another. So it will just give you the argument back. That was one of our properties of logs if you go back and look at that. So by doing this, by raising both sides as a power of 2, I would get 2 to the log base 2 of x squared over x plus 12 is equal to 2 to the power 1. And like I said, the exponential and the log cancel one another out as long as you've used the same base. And you would end up with x squared over x plus 12 is equal to 2 to the power 1, which is 2. As that exponential and log are going to cancel one another out. From this point, you're then going to solve for x, which should be pretty simple at this point. So you're going to multiply both sides by that x plus 12 to give you x squared is equal to, it would be 2x plus 24 when you multiply it out. Get everything onto one side so that you can set it equal to 0. And then factor it, and you should find you would get negative 6 and positive 4. So your possibilities for x are 6 and negative 4. Now at this point you need to do the same thing that we did with the type 1 log equations and plug them back in to that original equation that we had here to make sure that all arguments are positive. If you ever end up with an argument that's negative, then we know that that particular x value cannot be used. So if we look here, our particular x values we had were 6 and negative 4. When x is equal to 6, all of my log terms have a positive argument because I would just plug in x is equal to 6 into here and x is equal to 6 into here. Both of my arguments are then positive. They'd be 6 and 18. When I plug in x is equal to negative 4, this argument here would just be negative 4. That's not possible. You cannot have a negative number as your argument. So that tells me that x is equal to negative 4 is not a valid solution because it makes one of my arguments in my original equation negative. So I cannot use that particular value. So my only solution is x is equal to 6. So it's very important. Go back and plug these into the original equation. And like I said, that means that x is equal to 6 is our only possible solution to this particular type 2 log equation. Now we need to look at some exponential equations. There's a couple different types of exponential equations that you will need to be able to solve. We'll do some simple ones first, and I'll show you a couple different things that you may come across, and then we will look at some more difficult ones that are going to involve some factoring. So the first one is a very simple exponential equation that looks very similar to things that we have seen before. And you have to solve 3 to the x equals 7. Okay, and you've got to solve for x. Now, whenever you get a problem like this, what I want you to do is to take either the natural log or the common log, so the log base 10, of both sides. Okay, what will that do? Well, at that point we can then use the exponent to constant property of logs, and that will let us solve for x. It doesn't matter which log you actually use here for both sides. You just need to make sure that you use the same one on both sides. And the easiest one to use normally is going to be either the natural log or the common log. I'm going to use the natural log here. So if I take the natural log of both sides, okay, then I can use that exponent to constant rule. So that means that the x will come down in front and leave me with this. And then the natural log of 3, that's just a constant. So I can divide both sides by the natural log of 3, leaving me with this. Now the natural log, that is a function. I cannot cancel it out here. Okay, so I've got a function of 7 divided by a function of 3. It just has to stay as it is. Okay, both of them are constants, but they do give us a function here. Even though you get a constant out of it, you can't just cancel them out. They're not variables. Okay, so we have to leave it like this. The same idea goes with anything that looks like this type of a problem. Okay? Another example that comes up in the textbook is where they have a number in front of that exponential. So we got 5 multiplied by 2 to the x equals 9. If you ever have a number multiplied at the front of that exponential, all I want you to do is divide through by it, and then you're going to use exactly the same method that we just used. So I'm going to divide both sides through by that 5. Okay, so if you ever get a problem like this, it's going to go the exact same way as we did the first one. So we're going to take the natural log of both sides or the common log of both sides, and then go ahead and solve for x using that exponent to constant property of the logs. But if you do ever have a number multiplying the exponential at the front, make sure you divide through by it first. And then we can proceed as we did before. So then I take the natural log of both sides, and then I use that exponent to constant rule. And then I can divide through by the natural log of 2. And like I said, it doesn't matter which log you use as long as you use the same one on both sides. The final type of problem that you will see that's very similar to this one is where you actually have an exponential on both sides. So this time we've got 3 to the 2x plus 1 is equal to 2 to the x minus 1. I want you to do the exact same thing again, okay? Take the natural log or the common log of both sides. We don't have any numbers multiplying at the front, so we don't have to divide through by anything, but we do need to bring those powers that have got the x in it, we need to bring them down, and the only way to do that is to use our properties of logs. So I'm going to take the natural log of both sides exactly like I did before. And what that will allow me to do is to bring down those powers to the front. So I'm going to end up with 2x plus 1 multiplied by the natural log of 3 is equal to x minus 1 times the natural log of 2. What I'm going to do then is to bring all of the x terms together and all of the constant terms together. So when you multiply this out, I'm going to get 2 times the natural log of 3 multiplied by x plus the natural log of 3 is equal to the natural log of 2 times x minus the natural log of 2. Then I'm going to bring anything that's got an x in it onto the left-hand side, anything else onto the right-hand side. So that gives me 2 the natural log of 3 times x minus the natural log of 2 times x is equal to negative the natural log of 3 minus the natural log of 2. Okay. Then I can factor out the x and divide through by the constant that I get. So if I factor out an x, I get 2 times the natural log of 3 minus the natural log of 2. And then on my right-hand side, you don't have to do this, but it's just something I'm going to do here. I'm going to pull out a negative just to make it look slightly neater here. So that will be a plus natural log of 2. So I've just pulled out a negative. Like I said, you don't have to do that, but it will make our fraction look slightly neater if we do this. So it's then going to be the negative of the natural log of 3 plus the natural log of 2 over 2 times the natural log of 3 minus the natural log of 2. Okay. So even though there's a lot more algebraic manipulation towards the end of this problem, the beginning of it is the exact same. Okay, you're going to take either the natural log or the common log of both sides. You're going to use that exponent to constant property, and then you're going to bring all your x terms together, all your constants together on either side, and then you can factor out the x. So whenever you get a problem like this, that's how I want you to go ahead and solve it. The final type of problem that you will see is where you've got to use some factoring, okay? These will always be in the form of a quadratic. I'm going to give you an example here. These don't come up as often, but you do need to be able to solve them, and you may see them occasionally in calculus, particularly in calculus 2. So I want you to be able to look at these and make sure you recognize them. Okay, that's because it uses a lot of substitution, and that's something that comes up in calculus. So whenever you get a problem like this, it will normally involve e to the x. Okay, they sometimes use other different exponential functions, but normally it's e to the x. So I'll do two different ones here, but the first one I'm going to do does involve an e to the x. So you're going to have to solve for x. E to the 2x minus e to the x is equal to 12. Okay. Whenever you get a problem that looks like this, okay, it doesn't look like the other problems that we had where we just had everything in terms of exponents equals a constant or two different exponents and that was it. For this one, what I want you to do is to bring everything onto one side and then treat it like a quadratic. So I'm going to bring everything onto one side. And now I'm going to solve this as though it were a quadratic. The way that I can do that is by rewriting my equation like this. And then what I'm going to do is use a substitution of u is equal to e to the x. Okay. Now what I want you to do is rewrite your equation in terms of u and solve it. So if we factor this, you should end up with minus 4 and plus 3. So either u is equal to 4 or u is equal to negative 3. Okay. Now, go back to what we used for our substitution. U is equal to e to the x. So that tells me that either e to the x is equal to 4 or e to the x is equal to negative 3. Okay, so that tells me that x is equal to the natural log of 4 by using the inverse of e to the x, which is the natural log, or x is equal to the natural log of negative 3. Okay, this one is totally fine. That's a valid solution. The problem with this solution is that we have a negative argument. Okay, remember the natural log is just log base e, but the argument is still negative. Okay, our argument is negative 3. Which we can't have when we look at logs. We cannot have a negative argument because e to the power of anything is never going to equal a negative number. So this is not a valid solution. So the only x that is a valid solution is the natural log of 4. Okay, so let's go back through what I did here. Okay, whenever you see a problem like this, treat it like a quadratic. Bring everything onto one side, let it equal 0. Then you're going to use a substitution, whatever it might be, in order to substitute in as a quadratic. So then you're going to end up with this quadratic equation that you can factor and solve for. Then you have to solve for x and then look at whether you end up with anything that has a negative argument. If you have a negative argument, then you know that that's not possible and therefore that's not going to be a valid solution. So only things that have a positive argument in them are going to be a valid solution. I'll do one final problem like this, and they've actually used a different base in this one. But regardless of what you have, as long as it's an exponential function, this will work. It's just that you tend to see these problems with a base of e. But we'll do one that has a slightly different base for now, just to show you how it works. Okay. Same thing as before, bring everything onto one side, and then we're going to treat it like a quadratic. So that's going to be 2 to the 2x squared. Okay, remember, you're going to multiply the powers. Whenever you take something to the power and then to the power of something else, you just multiply the powers. Minus 5 multiplied by 2 to the 2x minus 6 equals 0. So my substitution here is going to be u is equal to 2 to the 2x, leaving me with u squared minus 5u minus 6 equals 0. So doing that factoring tells me that I'm going to have negative 6 and plus 1. So I've got either u is equal to 6 or u is equal to negative 1. And then if I go back, okay, that tells me that I've got 2 to the 2x is equal to 6 or 2 to the 2x is equal to negative 1. I've got to take the log base 2 of both sides here. Okay, so if I do the log base 2, it's going to cancel out the 2 and just give me the argument on the left-hand side, and then I'm going to have log base 2 of whatever's on the right-hand side. So taking log base 2 of both sides will leave me with 2x is equal to log base 2 of 6, and 2x is equal to log base 2 of -1. And then I can just divide both through by 2 to leave me with x for each one. Okay. Only one of these is actually a valid solution, because here you can see we are taking a log with an argument of a negative number. Okay, so obviously that is not valid, so our only valid solution is this x value. Okay. So same as before, you treat the equation like a quadratic. You go ahead, do a substitution, factor it and solve. And once you've done that, you go back to your substitution and make each of your solutions equal to whatever your substitution was, solve for x, and then look at whether you have any negative arguments, which would therefore give you a solution that's not valid. So all of these kind of go the same way. You either are going to have that exponential problem like we had at the start, where you can just take the natural log or the common log of both sides, and it should be pretty simple to solve. If not, if you end up with an example like this, you're going to have to treat it like a quadratic and use some factoring in order to solve.